Welcome to lecture number 23 for ECE 476, Advanced Embedded Systems. In this lecture, we're looking at wind speed, pressure, and humidity sensors. Now, three more useful things that could be known and measurable with a Pi Pico is wind speed. That's important for airplane flight controls, for evaluating a site for wind turbines, and evaluating if conditions are right for fungus growth. Air pressure is useful for measuring or for controlling aircraft, for predicting weather, and measuring the wind speed with a pitot tube. And humidity also tells you how comfortable a given temperature is, or if the room conditions are okay for some plants and equipment. So how you measure that? That's what this lecture is all about. So what we're going to look at in this lecture is measuring wind speed three different ways: using a fan, using a hot wire anemometer, and using a pitot tube. We'll look at measuring air pressure using a BME or BMP 280 digital sensor, and measuring humidity using a BMP 280, DHT11, and DHT22 sensor. And there are other ways to measure each of these, but this gives you kind of an idea of some of the methods available to you. So let's start out with fan speed. One way to measure wind is by measuring the speed of a fan. Kind of the idea is if you apply a voltage to a fan, it spins. If you apply wind to a fan, it spins. If I can measure how fast the fan is spinning, I'll know the wind speed. And there's a couple different types of wind speed sensors. This is an omnidirectional wind speed sensor. Doesn't matter which way the wind's blowing. The harder the wind blows, it spins around. And the faster it spins. A directional one would be like a fan. Point that into the wind, and it causes the fan to spin. If I can measure the RPM, or revolutions per second, I have a measurement of wind speed. Either way, it's about the same result. If I can measure the speed of a fan, I can measure the wind speed. So there's a couple ways of doing that. Several fans have encoders. For example, this guy over here, you can see it. It's got 3 wires to it. 2 wires are power ground. The third wire is the speed sensor. What it does is that speed sensor is grounded for half the rotation. So what happens is if I ground the middle point, this guy is grounded half the time, floating half the time. Use a pull-up resistor, and what I get is a square wave. As the fan rotates, I get a square wave out. One cycle is one rotation. So if I can measure the frequency of the square wave, I can measure the speed of the fan. Kind of a sidelight. This is kind of how computer fans work. That third sensor is your speed sensor. If the fan is stalled, you get no square wave out. If there's no square wave out, you know the fan's not running. Shut down the computer because it's going to overheat. From our purpose, we just want to know how fast the fan's spinning. So easy way to do that is use a pull-up resistor. In this case, I'm going to use an internal pull-up resistor. Connect your fan to your favorite pin. I'm using pin 0. And then measure the frequency of the square wave. So this measures how long you're at a 1. This measures how long you're at a 0. Add the two together, I've got the period. Go 1 over the period, I've got the speed. So this is the high, this is the low. Take 1 million, because it's microseconds, divided by the period, I've got the speed in hertz. That's how fast this fan is spinning. If I slow it down, put my finger on it, I can see the speed is dropping. The last column is going down. It's running freely. I have a fan speed sensor. Have the wind spin that, and I've got a measurement of wind speed. A second way to measure wind speed is called a hot wire anemometer. Now the idea here is previously we looked at using a thermistor to measure temperature. And technically, you're not actually measuring the temperature of the air, you're measuring the temperature of the thermistor. if I have current going through the thermistor, it's producing heat through I²R heating. So what you're measuring is actually the heat of the thermistor. It'll be slightly hotter than the ambient, and I can calculate that. In the thermistor, there in the data sheets, it'll tell you the heat dissipation. That's in still air. This one's 3.5 milliwatts per degree Kelvin. So the more energy I'm dissipating, the hotter the thermistor is going to be relative to ambient temperature. For example, the previous thermistor we looked at 25 Celsius, if I supply 1.65 milliamps to it, the self-heating will be 2.7 milliwatts. At 3.5 milliwatts per degree Kelvin, it's actually 0.778 degrees above ambient. So when I measure air temperature, it's not actually air temperature, it's air temperature plus 0.778 degrees Kelvin. That's when there's no breeze. If there is a breeze, I get more cooling, and the dT will get smaller and smaller. So this is why they actually build thermistors of different values. They have 10 ohm, 1 ohm, 10 ohm, 100 ohm thermistors, small resistance. They have 100K, 1 meg thermistors, high resistance. The small thermistors have higher self-heating. For example, if I went to 100 ohm thermistor, then I'll have more current. More current means more I²R losses. With the larger thermistor, I'll have much less current. Less current means less self-heating. So the 100K thermistor will basically be reading ambient temperature. The 100 ohm thermistor is ambient plus self-heating. The stronger the wind, the closer these are together. So suppose I have no wind. I can calculate the power dissipated in the 100 ohm thermistor. That's V²/R. Have the voltage across the thermistor, assuming got 100 ohm, 100K resistor in my dividers. The 100 ohm resistor or thermistor is dissipating 27 milliwatts. The 100K is dissipating 27 microwatts. The self-heating then will be 7 degrees for the 100 watts or 100 ohm, 0.007 degrees for the 100K. This is basically ambient temperature. This is ambient plus 7. Well, if I'm 7 degrees above ambient, then the resistance will drop. The voltage will be different, and then the difference of voltage is a measurement of wind speed. So here I'm getting 0.2739 volts if there's no wind. The higher the wind speed, the smaller that voltage. To improve the sensitivity, I could use a whetstone bridge. Basically take my thermistors, take the difference in the two, amplify them with a differential amplifier. This is the difference times 10, that ratio. That gives me a higher voltage, so it's now 2.7 volts at 0 wind speed. Voltage drop decreases as the wind speed increases, as these get closer and closer to ambient temperature. That's called a hot wire anemometer, another way to measure wind speed. A third way is a pitot tube. So if I have a tube, one facing into the wind, one perpendicular to the wind, this is basically measuring static pressure, the pressure of the wind. This is the static pressure plus dynamic pressure. As you go into the wind to get some extra pressure, that's the dynamic pressure. The higher the wind speed, the higher the dynamic pressure. That pushes this part of the pitot tube down, that water level. The difference in height is a measurement of wind speed. From Wikipedia, the total pressure is the static pressure plus dynamic pressure. Dynamic pressure is a function of wind speed squared and the density of the fluid divided by 2. Solving for velocity, here's the equation for velocity as a function of the difference in pressure. So if we can measure the pressure difference, I can measure velocity. So for example, if I am going up to 30 meters per second, or 67 miles an hour, at 1 atmosphere, the density of air is 1.2 kilograms per square meter. The pressure difference then is 541 kilograms per meter second squared, or just in the units, the pressure difference is 541.8 pascals, or in 100 pascals, 5.400 pascals. So that's the pressure difference that you would see at 30 meters per second, 67 miles an hour. To put that in perspective, 1 atmosphere is 1,000 pascals. So that's 0.5%. If I can measure 500 pascals, I can measure wind speed. This actually works better at higher speeds. It's why it's used in aircraft, not cars. But it does give you measurement, and better when you get faster. So that's kind of some ways to measure speed. To measure pressure. Again, a couple of reasons to measure pressure is I need a pressure sensor to measure the pressure in a pitot tube, which measures wind speed. Pressure also gives you a measurement of the air pressure. Low pressure tends to be a cold front or a storm coming. High pressure tends to be more of a clear day. Ways to measure pressure. Some reasons you might want to measure pressure. With pressure, there's a couple different types of pressure sensors. There's absolute pressure, differential pressure, and gauge pressure. Absolute pressure is pressure relative to a vacuum. So if I have a vacuum right here, I want to measure the pressure in A. As the pressure goes up, this diaphragm flexes. If I measure that flexing, I've got the absolute pressure relative to 0. There's differential pressure. I can have the pressure in A, pressure in B, take the difference in the two. That'd be like for a pitot tube. There's also gauge pressure. This is the pressure relative to 1 atmosphere. So you can actually buy pressure sensors of all 3 types. You can get them with analog outputs. You can get them with digital outputs, either in SCI or I2C outputs. Well, the BME280 or BMP280 are 2 digital sensors that give you temperature, absolute pressure, and humidity with a resolution of 0.01. Those sensors also support I2C and SPI communications, and you get them on Amazon, GeeekPi, other places like that. In terms of the hardware, depends upon what interface you want. If you want to go with I2C communication, this is the hardware connection. There's also SPI. I'm going with I2C because I found solutions on the web for I2C communication. SPI, again, the Raspberry Pi Pico has only been out for a couple of years. I haven't been able to find any SPI communication for it. In terms of software, what you can do is you can dig through the data sheets, write your own, or hope that somebody else's written code to drive the sensor and use their code. Well, if you go to randomnerdtutorials.com, there are drivers for the sensor for the BMP280 using the I2C interface, which is why I'm using that. To do that, you need to go to that website, download the BME280 library, download the driver code, and then follow the schematics, basically the previous one, run the driver code, and you're good to go. You're reading temperature and humidity. So what that kind of looks like this is the BME280 code. You just copy it from that website. It's also on Bison Academy. And then save it to file save as. File save as. You've got to save it on the Raspberry Pi Pico somewhere. There it is, BME280.py. I can then take the driver routine. I have to import BME280, it needs to be on the Pi Pico, define an I2C interface. I am connecting it through pins 4 and 5, communicating at 10 kilohertz. I'm then going to read the BME280 using I2C interface, pull off the temperature, humidity, and pressure, and then display it. So here's what that looks like. I've got the sensor connected. If I put my hand over it, see the temperature is going up, pressure's not doing much, and the humidity is 0. That's because I'm using a BMP 280 chip that doesn't have humidity. Use a BME 280 chip, you'll get humidity as well. Good to 2 decimal places. With that, I've got temperature, humidity, and pressure. If we go to this website, it's actually a rather nice tutorial on using it. There's a sensor. That's the BME versus BMP connections. Here's the code that you need to download. I've got a reading for temperature, pressure, and humidity. There are other humidity sensors. There's the DHT11 and DHT22. Now these are listed as being obsolete on DigiKey, probably because they're being replaced by the BME 280. But the drivers are included in MicroPython, so you don't actually have to go find them. The specs on these two sensors, these are really about the same. The 11 is blue, the 22 is white. They both operate between 3.3 and 6 volts. They measure relative humidity from 0 to 100%, temperature from minus 40 C to plus 125 C, and the resolution. The 11 has a resolution of 1 C or 1%. The 22 has a resolution of 0.1 C, 0.1% RH. The BME 280 is 10 times, 0.01 C, 0.01 RH. In terms of wiring, they're both the same. You give it power, ground, and the output pin needs a pull-up resistor. Not really needed if you use the internal pull-up resistor on the Pi Pico. What the communication looks like, if you look at it on the oscilloscope, I take the output pin, pull it low for 500 milliseconds, high for 20 milliseconds or microseconds. Then the sensor takes over and transmits 5 bytes of data. Each byte has the ones and zeros encoded. A logic 1 has a square wave which is high for 70 microseconds. Logic 0 has a square wave which is low for 26 microseconds. Now, if this is 376 embedded systems, we could write an assembler or C routine to pull off the bits one by one. In Python, you don't really need to do that. I just need to import the library DHT. That's got the driver routines already written for you. DHT has these functions. If I do help DHT11, this tells you the humidity and temperature. To read a DHT11 sensor, I need to import DHT machine and time. Tell it the sensor is connected to pin 22, and then take a measurement, pull off the temperature, pull off the relative humidity, and display it. So if I do that, here's a DHT11, import it, pull off temperature, humidity, display it. There's the humidity, temperature. This is a DHT11, the blue one. Put it in my hand. See the temperature is going up. Humidity is going up. I've got a humidity and temperature sensor. Do the same thing with the DHT22. I get an extra decimal place of accuracy. Otherwise about the same. That's one of the beauties of using Python. If you can find the driver routines in a library, they're pretty easy to use. I just have to import that library, call those functions, and I've got the sensor. That's also a problem with the digital sensors, is if you don't have the library, you got to figure out how to write it yourself. But with those, with the DHT sensor, BME, BMP sensors, I can measure temperature, humidity, pressure of the BMP sensor. And they're really not that hard to read. These are digital sensors, so you need the driver routines. But given the driver routines, measuring wind speed, air pressure, humidity, it's actually fairly easy, especially if somebody else has written the driver. And that's lecture number 23 for ECE 476, Advanced Embedded.